Уважаемые коллеги, еще раз здравствуйте. Приносим извинения за задержку в 10 минут. Мы начинаем наш форум, конференцию, посвященную программному комплексу SOFiSTiK. И у нас достаточно много сегодня интересных вещей для того, чтобы рассказать вам. И скажу, что сам семинар будет разделен на 3 большие секции. Это мосты, гражданское строительство и геотехника. И для вступительного слова на нашем семинаре я предоставляю Борису Алексеевичу Воробьеву, заместителю генерального директора компании ПСС. Прошу, Борис Алексеевич.
Уважаемые коллеги, дамы и господа, очень приятно вас поприветствовать сегодня в нашем зале. Подвела транспортная ситуация в городе Санкт-Петербурге. Я надеюсь, что те, кто хотел, сегодня еще подъедут. Мы сегодня в нашем зале приветствуем тех, кто приехал издалека, прежде всего, из солнечного Казахстана, из независимой Украины, из союзной Белоруссии и из цивилизованной Европы, из стран Испании и Германии. Сегодня мы хотели устроить такой небольшой праздник. Вы знаете, что у нас есть профессиональные праздники там, для строителей, для доярок, там, значит, а вот для расчетчика нет. И вот мы решили, что надо восполнить этот пробел и своими силами эту систему устроить такой праздник расчетчика. Один день. Мы только говорим о конечных элементах, о расчетах уникальных зданий и сооружений, такие как Вахта-центр, Зенит-арена, которая будет в 2018 принимать чемпионат Европы в Петербурге, и других объектах мирового уровня, которые, я думаю, интересны будут каждому инженеру, как они решаются эти задачи и конструктивно, и в расчетном плане. Для нас важно, чтобы все, кто уже использует, начал использовать SOFiSTiK, или те, кто думает, догадывается, понимали его особые, исключительные возможности, которые отличают этот продукт конечно-элементного анализа от обычных, среднего уровня, которые принято использовать у нас в Российской Федерации, в наших странах СНГ. Это очень изящный и углубленный инструмент для углубленного анализа конечно-элементных моделей. Он позволяет решать не просто задачу, как ввел, так и получил, но и решать какие-то оптимизационные решения, искать какие-то более эффективные конструктивные решения. И я надеюсь, что наши гости, приехавшие из Испании, профессор Hugo Corres из Испании и из Германии, доктор Йорк Йонгвет, поделится с секретами, как это делается в Европе. Для нас важно сегодня организовать хороший диалог. И для этого мы не только заседаем здесь, в этом зале. Здесь также в фойе, как вы видели, устроены стенды, где сидят консультанты, которые разговаривают по-русски. И вы можете к любому из них, в то время, когда вы считаете удобным, подойти. Они будут постоянно там находиться и обсудить любые вопросы. Там также все разделено по, так сказать, направлениям деятельности и по объектам проектирования. И для того, чтобы сделать еще более эффективным и тесным контакт с Европой и практически слиться, у нас есть еще переводчиков, пожалуйста. Прошу любить и жаловать. Значит, вы можете воспользоваться его услугами в течение всего дня до окончания конференции. Для того, чтобы воспользоваться услугами, для того, чтобы произвести переговоры с представителями Европы, которые не говорят по-русски, вы должны обратиться либо на регистрации, либо ко мне. И тогда мы, так сказать, организуем процесс, так сказать, этих переговоров. Ну, у меня пока все. Желаю успехов. Я надеюсь, что этот диалог приведет вас к новому пониманию тех уникальных возможностей, которые предоставляет европейская программа обучения конечно-элементного анализа.
Спасибо большое, Борис Алексеевич. Микрофон буду передавать нашим докладчикам. Итак, конференция «Мировой опыт использования SOFiSTiK», первая международная конференция такого масштаба в России, мы объявляем открытой. И для первого доклада мы приглашаем сюда профессора, доктора Hugo Corres, который поделится опытом применения ПК SOFiSTiK в Испании. Пожалуйста, профессор доктор Hugo Corres.
Thank you. Good morning, everybody. It is a pleasure to me being here with you. So I will speak about engineering and SOFiSTiK. I need some. Okay, here. Well, oh yes, it's okay. So I will start with this amazing structure. At that time, it was built in the 2nd century, and at that time they have not SOFiSTiK, unfortunately, but they were able to do incredible, amazing structures, and they were able to, of all the materials, and they to use all the materials in the right to produce this very interesting structure. This one, the Pantheon in Rome. Unfortunately, they have freedom because they didn't have codes, they didn't have checkers, they didn't have many things. So they were able to really create new structures. So, and the result was the following. Here you have the Pantheon, which was built in the 2nd century, and this St. Peter's dome was built practically 1,400 years later, but the size, the diameter of the dome was exactly the same, more or less. So this structure is very, very interesting, plenty of ideas, and we need that. We need to use well the tools we have, but we need to have good ideas. This is very important. Our first SOFiSTiK was a bridge, a competition in 1989, more than 20 years ago. And we bought SOFiSTiK at that time because we wanted to take advantage of non-linear geometrical calculations, because you know that a bridge like this needs geometrical non-linear analysis. And this was the reason why we started working with SOFiSTiK, but I will not tell you about bridge. It happened many years ago, and now I will show more recent projects. The first one, he died 2 years ago. He was Oscar Niemeyer, a very well-known architect from Brazil, and I met him when he was 101 years old. I took that picture myself, and I was talking with him, and for me it was very interesting, the interview, the meeting we had, because he had passion to produce, to build, to design, and he had this project, and we were making the structural design of all these buildings. And here you have the result This is the real situation of the different buildings, and you see there is a very good similarity with the model, and this is very interesting too. And I will concentrate in this building. Here you have a cross section. I will give you some details, and there is this is a concrete. It's not a shell, but it is a concrete slab with a shape a little bit strange. And we made this model because we wanted to reproduce the different elements which were not so clear to see from the first contacts with the structure. And you see we made this complicated model, and representing all the different details. And I only want to say that at the end we had some estimations. The calculations we did in this case were linear in concrete, and you know that concrete cracks, and concrete has a non-linear behavior, and you need to pass from stresses or from forces into reinforcement, and this is not so simple to do that, and you have to really have a good way to get the information you can produce with a model like this, and to transform this information into design, into reinforcement, into all the different definitions you need. And here you have the final result, and we will talk about this transformation a little bit later. Here you have the reinforcement in the transversal direction, and the previous drawing were to indicate the reinforcement in the longitudinal direction, in the top layer and in the bottom layer. So the final result is this one. It's very nice. And we used also SOFiSTiK for some other models. For example, this element, which is very interesting. Conceptually, is very well known that this shape is very convenient, and you can take advantage of the shape in order to make good designs. But we wanted also to reproduce this special structure, and here you have the model again and the reality. Well, so you can use SOFiSTiK in concrete. Here you have another interesting structure. This one. Oh, this one, yes, and it's more or less the same concept I showed before. And and here you have the model we made in SOFiSTiK. So SOFiSTiK is a good instrument for concrete. We don't use SOFiSTiK for every type of structures, but we use for special cases in which we need to combine linear finite elements and shell elements, and we need to really reproduce complicated shapes. And the result is very good. You see, this is very important. Well, This is another completely different problem. This is some information we presented in a competition in Norway. It was a competition for a pedestrian bridge to cross this river, and we won the competition. And these are the ideas we had for the competition. You see that is a stress ribbon pedestrian bridge, and this was the idea we had. But we made many other different proposals, but it is very important to understand well the information and the boundary conditions. And when I went to Norway to visit the place, I realized immediately that this type of solutions, the suspension pedestrian bridge or the arch proposal, were not very good for that pedestrian bridge. So we decided to develop this stress ribbon proposal, and we did that. The idea was at that time, you know, that if you have this type of structures, you have some problems with the slope for the users of the pedestrian bridge. So for that reason, we have, and here you are not able to see, but we have, you can guess that the depth of the stress ribbon is not constant, is a little bit variable in order to minimize the impact of the slope. And fortunately, we won this competition. You see here different pictures. And we needed to make the construction project. And the construction project, as you probably know, you need to adjust many things, but the final proposal is not so different to the initial one. But we decided to adjust a little bit better the slope evolution of the layout of the stress ribbon proposal, and we decided to abandon the idea of variable depth, and we have now this proposal, which is more typical. So this is a very interesting structure. You need to anchor cables in the abutments, and here you have the definition of the abutments. The abutments are very important elements because you have to get all the forces there. And here you have one abutment, which is anchored to the rock we have in this area, and I don't know, in this area, yes. And here you have some details. You need to accommodate all the anchor blocks for the anchor elements. And then the first part of the stress ribbon is a little bit thicker. And then you have these elements which are constant depth, and you need to install first some cables, the bearing cables, and then you need to install the segments, and then you need to cast these ribs, and then you can pre-stress some additional cables. And this is a very non-linear problem because geometrically non-linear problem and mechanically non-linear problem. So from the beginning, we decided to use SOFiSTiK. And well, I like to show this because after making interesting calculations, you have to produce very good details. And here you have the, this is a local detail of the segments. And here you have the bearing cables you install before the segments. And here you have the pre-stressing cables you pre-stress casting after casting this part of the segments. So the construction process is very difficult because you need to build the abutments as are indicated in these two steps. And then you need to install the cable, have to a good geometry because then you are not allowed to move or to increase forces in cables. And then you install the segments and you produce a big deformation in the cable. As you make the continuity between the segments, the precast segments and the cables, and then you pre-stress with the second system of cables, and with this pre-stressing you can elevate all the stress, and then you have losses in the pre-stressing, so you have some new deformations, and you the temperature which make the elongation of this element, and then to take into account the ultimate active are the cables. So you see here is a summary of the calculation. The model is not so complicated, but the concept is very complicated. Okay. Now it's better? It's not better? Yes. Yes. Well, and here you see the model. It's a simple, and here you see the model, and you can see also the forces. I will not explain in detail all these forces. I only want to give you an impression about the model we were using. So the model at the first is a cable. You can do that easily by hand to estimate the deformation. But here you see how the deformation is very small, 20 centimeters, because here you have only the weight of the cable, the cables, the bearing cables, and together with the pre-stressing forces. And the pre-stressing forces are very high, 10,000 kilonewtons. And then you install the precast elements, and you again have the same model, is the cable, and you will increase due to that load up to 3 meters, 2 meters and 70 centimeters, the deformation of the cable. And this is a non-linear behavior, but is again easily to follow by hand. And then you cast this part to give a monolithic behavior to the bridge, and you increase a little bit more the deformation up to 3.3 meters. But when you have the concrete with enough strength, you can introduce the pre-stressing. And this is not so easy to represent with the model, because you have to make some assumptions, and you need to change from a model in which you have cables to another model in which you have another completely different stiffness, because the stiffness in this second situation is the stiffness of the whole concrete cross-section. So to do that, you need to create a new model, and you need to pre-stress that new model in order to obtain the same deformation. You see here that you have two different models, but the deformation is exactly the same. So you need to start from the same situation, but with a different stiffness. And then you can work with this second model, in which you introduce the pre-stressing, so you elevate the bridge from 3 meters, 0.3 to 2 meters 70 centimeters. And then you need to take into account the losses, and when you have losses, you diminish the forces, and the forces and these situations increase the deformation. And also, if you have some heating due to the temperature, you increase the length of the pedestrian bridge, and you see that the movement is very important from practically 80 centimeters from the hotter situation to the cooler situation. So you have an interesting movement. And then you have the ultimate limited state, in which you don't have any more the contribution of concrete. You have only the steel, and you need to change again the model in order to take into account that situation. So in order to use very interesting and powerful program like SOFiSTiK, you need to know well which is the final result of your model. This is very important. You need to make a big effort in order to understand. Understand is something very important. It's the most important. More than to have a big model, a nice model, plenty of colors. To understand is the key aspect to really take advantage of a model or of a program like SOFiSTiK. Well, this is another completely different project. I have only two more. This one is one of these. And this is a roof over a stadium yard. Is in Marseille. You have been there 2 weeks ago. I will show you a picture I took personally 2 weeks ago. And the idea was made by architects. We were not able to work with them together in order to improve and to take advantage of the shape in order to minimize and optimize the behavior of the structure. And but our client is the constructor, and we needed to make a new proposal to optimize the quantities. And so we had ideas first, and then we needed to study carefully the nodes, because we, according to the codes, the Euro code, you can make a simplified calculation for a joint like this, made with tubes. but when you use very thin tubes, you could have buckling problems, and in those cases you need to make buckling calculations, and we made that type of calculations with SOFiSTiK. And you see here the model and the results, and we were first making, and you will see many manual calculations, and then when we had the order of magnitude of the problem, we started using SOFiSTiK to see carefully the details. But it is very important to know the order of magnitude of the results. And here you have another view of the model and the results. And here you see the reality. Reality is very important. You don't have any more models. You have reality. And this is reality. And this is reality. And this is another completely different view. If you really are close to the site, you see that models, are instruments. But at the end, you have to, you have all the responsibility of this roof has a diameter of 250 meters. It's not a small structure. So you need to be sure, and you need to use these tools in a very good way. You need to take advantage of the tools, but at the same time, you need not to forget that you are an engineer. You are obliged to understand. And well, you see, it's a very, very complex structure, I can say you. I was suffering more than 1 year now. It's almost finished, and you smile. But during the process, the system is completely different. But I would like to show you that always, these are all the calculations made by hand, and then they were the estimations. And we had first all these estimations before starting working with the model. And here you have the model, and here you have again. I like very much to make these hand calculations, and the model again, and reality. And reality is complex. It's a very, very complex structure. So SOFiSTiK was very useful to analyze this special problem, buckling, local buckling, and allow us to save a lot of money because we were able to use very thin tubes in order to solve this complex problem. So this is another example. You see the scale of the details in order to give you one idea. And I will pass quickly because I want to have time to show you the star of our project with SOFiSTiK. So, well, this is the one of the, there were another complication because we needed to build this roof. At the same time, they were using the field for every 15 days. We need to prepare a report to say you are able to play the next game here. So, and this is the situation. This picture was taken by myself 2 weeks ago in Marseille. So we are practically at the end. So now we are very happy, we can smile, but you suffer a lot when you do things like that. Well, I would like to finish my presentation with this last project. This was an interesting structure because you have here It's a pedestrian bridge, but at the same time it's a building because it's an exposition area. So you enter, you cross the river and you can see some exhibitions here. And this was built in Zaragoza, in my country, in 2008. And the winner of this competition was a very well-known architect, Zaha Hadid. And this was her idea. She is a very good architect, but a very difficult one. So you see, the definition of the bridge was this one. We had only that definition. Many cross-sections coming from Rhino. Rhino is a 3D CAD program, and they can do everything with Rhino, but then you need to make possible this structure. So and here you have another picture of the model. We participated in that competition too, and this was our proposal. Unfortunately, we lost. But it is very interesting to lose, because in many occasions when you lose, you learn. And if you learn, you have opportunities for the next one. So this one was our proposal. I will not explain you into details. We worked with Richard Rogers, and we had some initial ideas from classical buildings and structural ideas. I will not explain you in detail, but at the end we made a proposal and Zaha won. And we had our second opportunity because there was another competition for the construction of the building, and we had the opportunity to improve the structural design. And during that competition, the construction competition, I was practically 1 month thinking about the behavior of this very strange structure. So I made, all these are my sketches. I have a blue notebook, not this one. I have this one. And I made all my calculations here, really. I like to do all my calculations here. It's square, because engineers are a little bit square. It's blue, because we can make elegant. And it has some movement, because we are thinking all the time. So many good ideas behind the notebook. Well, I started thinking what to make possible this strange structure. And I thought, well, this is a beam, a very strange beam with 2 spans, 125 meter one, and 150 the other one. And you can think that the behavior is like this. And my first idea was, well, I will use the bottom part to resist the forces, and I will introduce all the top part not collaborating with structurally. But at the end, that was not possible, so I needed to rethink a little bit more. And I thought, well, we have some elements on the top of the top part of the building, and I will use this as structurally, and I will use also this mesh to pass the shear forces from the bottom chord to the top chord. And well, we started working in this direction. And you see that every single idea was checked with the strata and tie models. And in order to represent a very complex, this very complex structure. So we needed to use again SOFiSTiK because SOFiSTiK is our is the program for very difficult problems, I can say. So you see here we have this bottom box, steel box, and then we have this top cords, and we have this connection between the top cord and the bottom cord, and we made many different models. And here you have the model we did with SOFiSTiK. It was very realistic, but the model was done after understanding the problem. The problem is very, very important to understand the problem with simple calculations. Otherwise, you don't have any control, And you see that we like also to make calculation. We do simple calculations. We understand the flow of forces, and this is very important. When you know the flow of forces, at the end you know more or less the order of magnitude, and then you can check with more sophisticated models, and you have reality again. You need to do things to reach this level. And here you have the model we needed to reproduce. It was not, we were not able to reproduce all the details. We needed to make previous models in order to see how to simplify the general model. And I want to make you clear that before the models, we need ideas. Ideas are very important. And well, this is a very good example. We started with the ideas, and then we made a 2D proposal, and then we started checking these 2D proposals with 3D because the problem was so complex. It is not possible to imagine that you are making a good assumption only with one node, and then we needed to produce our proposal and then reality. And we made many different small models in order to understand the behavior of these nodes well. And at the end, these are from my notebook. Not this one, because I have a lot, but the books I had in 2007. Well, and but at the end, you see that we had many different models. These are local models to analyze the behavior of this node, in which you have the main cord, top cord, and then is divided into two legs, and the shape is completely strange, and so and so. But at the end, this is the diaphragm for the abutment. But you can see that many, I studied in Stuttgart 40 years ago, and I learned, I understood well this model, so I am using all the time strut and tie, not only for concrete, also for steel. Well, but at the end, we needed to build this bridge, and this is, here you have the river, and here we need a temporary peninsula, and we built the more complicated, geometrically more complicated part here, and we needed to build the second span here and launch. And the geometry of this bridge was so complicated, so we needed to do that in a very complicated way. And we were building this part, and here you have some pictures, and here you have the position of the part we were building outside of the river. And at the end, we needed to launch. And this process is very complicated. First, we needed to know the center of gravity of this part, and it's impossible to imagine where is the center of gravity of that part. And for doing that, you need to have a good model. You need to represent all the details in a good way in order to estimate the weights in a good way. And this was our first commitment for this model. And then we needed to support the bridge because the way of the launching was straight, but the bridge was not straight. So we needed to support the bridge with some auxiliary elements. You see these beams, and you needed to change the position of these legs every step. And here you have one picture in which you see which was the situation at the beginning of the launching, in which we measure the weight and the center of gravity, and this was an important moment. After seeing that our mistake was 80 centimeters, we want to celebrate with a good bottle of wine, Spanish wine, because 80 centimeters in a bridge like this is a very accurate calculation, really. and well, we need to know that we need. It's finished. 3 minutes. Okay, I will finish. I am well. I want to say that we took advantage of these legs in order to measure the forces we had in every step, and we have some. We were monitoring the process all the time with this simple instrumentation. This is very important to have good ideas to make simpler things. And well, at the end, you see here how difficult was to support in this position the bridge. At the beginning was in another completely different situation. And I will show you quickly because I have only 3 minutes, even less, 2 minutes. And you see, the bridge was supported in many places, and then we take the load with the jacks, and then we started the launching, and then we had in this position, but we needed to move laterally the bridge also in this direction, because you see we had some installations, very expensive installation we were not able to use for this, so we needed to do more complicated the problem, and well, and we continues. It is very interesting. You see, in certain moment we were not able to continue with the same system, so we needed to install this stay, and we needed to install this stay in order to. This one was to retain the launching, and this one was to support. And this is very important because if you lose force here, you increase the forces in this part of the bridge. But if you this load, the load handled by the cable is too much, you decrease the load here, so you don't have problem in this area, but you have problem in this area. So we needed to really follow the process. Here you have the temporary pylon, 40 meters height, you see here, and these are the and these are the back cables, and you have this was the way of the direction of the launching, and you see the bridge. I like this picture because you can see the geometry, the real geometry, which was very complicated, and we needed to launch the bridge in this line. And well, you see, we were able to do that. You can follow a little bit the process. And we made this launching in 1 month, and we were suffering. It was very, very, very difficult. And finally, you arrive to the place, and here I am. You see, my smile is very clear. I was happy. So, and then at the end, we needed to situate the bridge in the right position, and this process was complex. And here again, SOFiSTiK, because SOFiSTiK was the program we were using to study each position of the launching. And then at the end, we needed to join these two different parts, and we needed to add all the connections, and the connections were not so simple because we started connecting the bottom part and then the top part. So SOFiSTiK was very useful for this very complicated project. And here you see the final pictures, and here you see how Saja wanted her bridge during the competition, and how similar is the reality. And well, and here you have again our SOFiSTiK model with the reality, which is close. And well, I am finishing. This is my last, but let me say two things. It is very fascinating to design, but you need to suffer a little bit, and you need to understand a lot. Understand, and understand. And you learn this process with experience. You need not to lose any opportunity, even if the project is a simple one. You need to take advantage. For that reason, for me, it's not necessary to have a big project, an important and complex project. We need to make from each project a great project. Thank you very much.
Thank you. Спасибо, доктор Hugo Corres. Как было рассказано, SOFiSTiK решает огромный спектр задач. И в чем он особенно хорош, это в решении, как неоднократно повторял доктор Hugo Corres, нелинейных задач, сложных задач, специфических задач. У нас, к сожалению, не осталось времени сейчас на вопросы, потому что мы сейчас будем слушать следующий доклад. Но если есть вопросы к доктору Hugo Corres, пожалуйста, задавайте через нашего уважаемого переводчика, которого вы можете найти в зале.